Okay, hello everyone. We are here for a 2.5-hour free seminar, Solution Architecture Practitioner's Guide, or really core elements of solution architecture. So we'll take a look at what is solution architecture, I guess you'd call it, and then look at some sort of core and common solution architecture methods. What do we do in solution architecture? And in that, we'll talk about things like drawing boundaries, things like documenting the data flows across boundaries, things like decomposing a system into its constituent parts, and thinking about how do we know how to decompose the system and what sort of parts do we design. These are kind of the challenges of solution architecture. And then in Chapter 3, we're going to sort of take a look at how do we build applications in 2018 and onwards. And so we'll talk a little bit about rich internet applications. And that terminology itself is starting to look a little dated, but you sometimes hear just 4-tier applications or thin front-end applications, but we'll take a look at sort of how we put things together in the current time frame, and also take a look at a little bit about cloud operations designed for failure, distributed systems, and DevOps, and a little browse over virtualization and containerization. So I think you find it to be an interesting little outline or background on solution architecture and how we do solution architecture, what sort of things we undertake at the present time. So with no further ado, let's dive in. Not sure how many people we are going to end up with. We've got 95 attendees so far, so that's pretty impressive. I'm always very happy with this. If you want to ask questions with 95 people, I got to be a little peremptory about how many questions I can answer, but certainly feel free to drop a question into the questions panel. And with a bit of luck, I'll get to it without any further ado. I'm not going to go around the room and ask 95 people to introduce themselves, but thank you for coming anyway. So we are here for you. All right, so let's dive in. By the way, my name is Greg Trasuk, and I've been with WebH for total of about 18 years now, full-time for the past 10 years, and in previous lives did quite a lot of distributed systems design and sort of early cloud architecture. I claim to have invented microservices. Well, I think I can make a reasonable claim to that based on some work I did on a particular operating system back in 1985-86 kind of framework. Never wrote it up though. I should have told people about it. But I've got kind of an ingrained knowledge and understanding and feel for a lot of the architectural trends which have been sort of coming along on the mainstream in the past couple of years. So that's kind of an interesting outlook, I think. Just gonna, excuse me for a second, I'm gonna expand my questions window here. I think maybe more. Okay, perfect. All right, so what is solution architecture? I guess the first thing to kind of narrow down is what exactly do we mean by solutions architecture? And we often sort of put this in the context of enterprise architecture, solution architecture, and then technical architecture, where we would often say technical architecture kind of decomposes further into hardware and software architecture, or software architecture and network architecture, depending on how specific you want to get. The basic idea, the grand picture of things is that enterprise architecture is about looking at the overall enterprise, looking at and what's an enterprise? Well, we get into kind of recursive definitions here. An enterprise is a group of people or associated entities that's big enough to have some shared goals. Okay, and that could be your Boy Scout troop. It could be the accounting department. It could be the entire corporate entity in your corporation. So we often tend to think about enterprises as very very large companies, but it's not really a definition in terms of physical size. An enterprise is just a group of people or entities big enough to have some shared goals. And then enterprise architecture is all about how do we satisfy those shared goals or address those shared goals, and what technology is appropriate in what areas, and realizing that most enterprises are diverse enough. Even though we sort of use a minimal definition, we think of an enterprise as diverse enough to be doing some different things. Even your Boy Scout troop has got some camping activities and got some educational activities, and maybe there's a band. I sometimes use the example of one of my hobbies is amateur radio, and even our little amateur radio club in town is an enterprise scale thing. We've got educational activities. We're trying to teach new people about ham radio, and then we've got operations where we're running radio infrastructure for the county, and we've got a repeater shack up on the mountain just outside town, so it can cover all of the city. And that repeater shack happens to have 5 different CPUs in it, and along with a whole whack of communications equipment. So that repeater shack is actually a remote data center that we manage with Ansible scripts and stuff. So any sort of group probably has some different interest areas and a different set of what we call business problems to solve. So I would say enterprise architecture is about, or probably best expressed in terms of its goals. Question. Can we get a copy of today's session recorded? It is being recorded, so I believe there will be a copy available to you after the session. So yeah. Oh, and the other question is always, can we get a copy of the slides? And you should have actually, I think, a lecture book that was either sent out to you in advance or may be available for download. There's a handout little panel there. So yeah, all that's available to you. Anyway, so the goal of enterprise architecture is, number one, to have a functioning business. Okay, so the enterprise is doing something in the real world to satisfy its shared goals. And then we are utilizing appropriate technology solutions in service of that business goal. So, I sometimes shorten that to saying that the goal of enterprise architecture is to have a functioning business supported by appropriate technologies. And, that enterprise may change over time. The nature of any sort of group of people with shared values is that those shared values changes over time. Maybe we decide that, the education part is going to be more important than the operational part, or maybe we decide that, we're opening up a new service of, emergency management, who knows. So the goals may shift over time, and that is, sort of leading us to the idea that the architecture of the enterprise, the solutions that we use, the sort of appropriate technologies that we deploy will also shift over time. And enterprise architecture is all about making sure that they come together. Software architecture, hardware architecture, technical architecture is kind of easy to put your fingers on too. That's, how do we build an application? What software technologies and techniques do we use? Are we using object-oriented design? Are we using a functional language? Are we, using a distributed design? Is it, a distributed shared value store, whatever? That's how do we put the, how are we building these things? Okay. And in between there, and of course the sort of hardware side is how do we connect all these things together and what's the hardware platform that things run on. I'll just put it out there that in enterprise architecture, it's not that hardware architecture is not important, but it's less specific to the particular enterprise. So most of our sort of, networks and hardware and so on, we tend to just buy the services of having them configured and so on. So, when it comes to enterprise architecture, solution architecture, and technical architecture, we tend to focus a lot more on software architecture in the IT area because we're concerned about software and applications. Anyhow, so in between the how do we write a program and what's the right technologies to apply for our business goals, in between there is the idea, how do I have a bunch of programs that satisfy a particular area of my business goals? How do I satisfy those business goals and knowing that there's going to be software and so on involved? That's where solution architecture comes in. And so solution architecture is typically thought of as, how do we design a set of programs or a set of applications that solve a business problem and are in a position to, sort of evolve with the business problem, right? Solution architecture, any architecture often comes out of sort of a dissatisfaction with the status quo. And so, an architecture inhibits or enables the system's driving quality attributes. Is it up and running? Does it have the capacity to service all the requests that we need? Is it maintainable in the future? Is it, if I run into a bug, can I find out what happened? That's a question of inspectability and administrability. The decisions made in the architecture allow you to reason about and manage change as the system evolves. And, in some ways, the architecture is a high-level view or a high-level understanding of how the system is organized. It sort of lets you comprehend the system from the top down. Documented architecture enhances communication among stakeholders. If we can talk about what the components do, then we can discuss them. And so architecture is, in some ways, not necessarily about directing what sort of design you have, but knowing what designs are out there, what possibilities are out there, and sort of being able to have conversations about it. And quite often we find that, and we run into this with like design patterns and architectural patterns and so on. It's, talking about the message passing pattern or talking about the, the distributed shared value store pattern. Or the whiteboard pattern or what have you. It's not necessarily saying that, you're not selecting from a catalog of what to design, but if we can describe something, then we can talk about what the usual effects are of doing something that way and what some of the alternatives are. So it enhances communication among stakeholders. The architecture is a carrier of the earliest and most fundamental, hardest to change design decisions. And we've all had the experience of coming up against a, some decision that was made earlier in the project that, and sometimes even in the very first days of the project or hours of the project, that eventually causes the whole thing to collapse. And, the architecture is one of those early decisions that we kind of would like to get right. Architecture defines a set of constraints on subsequent implementations. And this is, sort of feeds into another purpose of architecture in general. And I just comment, an architecture, in particular an architectural framework, and we see this very much in software architecture, so that's, if any of you are coming from sort of application design background, you probably have some resonance with this. Architecture is largely about non-functional requirements of a system. The functional requirements of I can enter a number from an invoice and print a check, or send an e-payment. Those are functional requirements. That's describing what the system does. And, you know, developers are good at that. Developers are good at implementing functional requirements. You know, you can talk about how, you know, I have to take the number and I have to apply it to a couple of different accounts and make a couple of database transactions and then send a batch to the printer. Well, okay, that's fine. Where things get messy and sort of where the rubber hits the road with software is the non-functional requirements. You know, being able to do that while handling 10,000 check requests an hour, or making sure that we have backups, and if there is a failure in the communication link between the Los Angeles data center and the New York data center, that you know, we're going to be able to recover within 20 minutes. Well, that's non-functional requirements, and that's where architecture generally handles things or steps in to deal with it. And so, the net result of that is that we kind of have a trade-off or a social contract almost between developers and architects, which is that architects set down a set of guiding principles and constraints and say, you know, you write your software according to this framework or according to fit into this architectural design. And the payoff is your non-functional requirements are handled, and you can deal with business logic, and you can deal with the functional requirements. And so, you know, in a lot of ways, that architecture sets constraints, right? We say how things are going to be implemented so as to maintain the non-functional requirements. It's all good. Architecture may dictate the structure of an organization or reflect the structure of an organization. I forget. There's a rule named after somebody, and I forget the name of the law, but somebody, you know, common sort of statement is, show me the architecture of your software, and I can probably describe the organization structure of your company. And, you know, so architecture, you know, reflects the organization. Similarly, decomposition that we do will reflect functional boundaries that are in the organization. And also, certainly development organizations are often built around certain architectural boundaries and architectural decompositions. And we sometimes see even operational boundaries or operational setups that are predicated on a particular type of architecture. Architecture can provide the basis for evolutionary prototyping, you know, by helping us to think out what we need to know most desperately and at the most core level in order to move forward. And then we can do a prototype of that core level and find out what we need to know and use that for input to subsequent design. Architecture can, you know, it's a key artifact that lets the architect and the project manager reason about cost and schedule. And again, the idea of work breakdown structures and project management often, you know, naturally reflects the architecture, because we split an architecture into modules and subsystems and systems. And that's just a natural work breakdown structure too. Architecture could be created as a transferable, reusable model that forms the heart of a product line, and you know, given solution architecture or an application architecture, you may find that you have large elements of reusability in that architecture. You know, if you're implementing your payment processing solution, well, you may find that it bears a lot of similarity with your internal cost accounting solution, and you know, you may be able to reuse some parts of the architecture. Architecture can be, architecture-based development focuses attention on the assembly of components rather than simply on their creation. And you know, anytime we talk about components, and we will talk about decomposing systems and thinking of components, but the whole point of that is abstraction. We want to deal with the external functionalities and the external modalities of using a thing without dealing with the internal details of it, you know. And I always kind of go back to, you know, if you look at electronics or computer system architecture, you know, a system designer that's putting a memory chip on a board wants to deal with the fact that, you know, the memory chip has a certain physical dimension, and has a certain number of input and output lines and a certain protocol that if you call up for this address and say I want 16 bytes and then hit the strobe or the clock line 16 times, you'll get 16 pieces of information. And as complex as that may sound, that's a whole lot simpler than dealing with the fact that, you know, at some subatomic level or nuclear or, you know, atomic level anyway, or some sort of microscopic level, you know, you're dealing with silicon that has little bits of gallium arsenide applied to it to provide N-channel doping, and you know, if you apply a little bit of a current or charge at this gate, it enables current to flow between these two other pins. You know, we deal with abstractions, and so architecture sort of focuses attention on the high-level functionality of components rather than, you know, the guts of the internals of them. And you know, by restricting design alternatives, architecture channels the creativity of developers, reducing system and design and system complexity. And this is kind of a funny statement I always find, but you know, to a designer, there's nothing worse than to look at a blank sheet of paper and get started. And you know, having a structure that you're working within quite often, you know, frees up a lot of mind power for doing something interesting within that structure. You know, and people say, well, I don't want to have a tightly scripted architecture because you know, then I don't have any flexibility to satisfy my design needs. And you know, I sort of point conceptually and philosophically to you know, some of you may be into music and you may be familiar with the 12-bar blues. You know, well, the 12-bar blues says I got 12 bars of music and, you know, chords 1, 2, 3, 4, and 5. Well, 1, 4, and 5 typically we use. And, you know, I got 2 bars of the 1 chord and then 2 bars of the 4 chord and then 2 more bars of the 1 chord and then 5 and then 4 and then turn around. Well, that's kind of a structure that's, you know, a little bit limiting. And yet, if you look at, you know, huge swaths of popular music and rock and roll, they're all based on that same structure. And what you find is that having a structure to start with then gives you the freedom to kind of innovate within that structure. And so architecture is much the same way. We can have a lot of, you know, the fact that there's a structure to start from then lets you experiment and do things within that structure. So it can actually speed up a lot of development to have some constraints, believe it or not. Okay. Communication vehicle among stakeholders. Well, this is one of the big things. Architecture gives us a common language that the architect can communicate with stakeholders and stakeholders can communicate with each other. This also reflects the idea that one of the architect's jobs, or one of the jobs of architecture in general, is to reach compromises or reach agreements between stakeholders. You know, we have, when negotiating requirements with users and other stakeholders, there will be a number of different stakeholders in any kind of project, and each stakeholder has different concerns and needs. And, you know, an architecture is designed to satisfy as many of those concerns as we can, and also to demonstrate and communicate that those concerns have been handled. So, you know, it's very useful for keeping the customer informed on progress and cost and implementing management decisions and also informing stakeholders about design decisions and trade-offs. Quite frequently, we end up with a project, you know, the actual implementation effort organized around architectural elements. And this is because the decomposition of a large system into subsystems and into components and frameworks within those subsystems kind of gives us a natural work breakdown structure. And so we can use that to organize both our, you know, artifact storage, our source code management, also the division into teams, the assignments to teams, the communication structure between teams, organization of documentation, libraries, testing is often organized around architecture. You know, we talk about component test and then integration test and then system test and then, you know, final quality assurance. Really, we're moving up the tiers of architecture. So, we use a lot of these terms, system, subsystem, module, component, etc. We use them kind of in a cavalier fashion. But it's often useful to sort of step back and do some definitions, right? So what is a system? Well, a system is kind of a term that can have a lot of meaning. We can use and misuse it in a lot of ways. But it can be the enterprise, could be, a particular line of business, could be segment architecture, an architecture that applies to a particular section of the business, could be an application, whatever. There are some, many definitions and many efforts to define architecture over the years. And I should point out, if you're the kind of person that likes nice, compact, well-stated answers, and if you really don't like ambiguity and you don't like sort of touchy-feely kind of questions, if that's the case, I'm going to suggest you might be happier pursuing a different field of work from system architecture or enterprise architecture, because it's you kind of have to get used to some ambiguity and talking about visions more than concrete things. But anyway, so a lot of efforts over the years to define things in architecture. The IEEE standard 1471, I believe it is, defines a system as a collection of components organized to accomplish a specific function or set of functions. And, what does that mean? Well, system practices relate to all system types. We talk about defining stakeholders in the system and then saying that each stakeholder has a set of concerns, and to communicate with those stakeholders, we have views and viewpoints that reflect addressing a number of concerns. So a system is, whatever it is that's big enough to handle some problem, or some system that handles a common goal. And architecture analysis and architecture decomposition focuses on structure. So why structure? Well, what we're focusing on, we treat the pieces of the system as black boxes. Okay, we don't want to get involved in details of what's inside those boxes. I often joke that architecture is all about drawing boxes and then documenting the lines that go across the edges of the boxes, or the connections between the boxes. And so that separates the structure, or separates concerns between the structure, i.e. the pieces, and the details of implementing the pieces, right? And, the implementation usually can be handled by somebody else, given the overall requirements of that piece. And so what we try to do, at the system level, is identify enough requirements of all of the components that you can do that parallelism. You can have someone go off and handle the design and implementation of a component, and have some reasonable expectation that it works when they come back. So suppressing the internal details of the elements doesn't affect how the elements are used or how they relate to or interact with other elements. It just says that we specify what the relationships are. We specify what the interfaces are. And the internals, well, I don't really care about long as they meet the requirements of the interfaces. So it makes the architecture an abstraction of a system, right? So simplification. So that when we're thinking about the architecture and asking questions about, can we handle the workload that we need to handle? Or can we maintain this, or when we survive a network outage in a particular area, we don't have to deal with the down and dirty details of the implementation. So we can focus on the higher level aspects. So solution architecture fits in, kind of in between enterprise strategic architecture and segment architecture and solution architecture. We focus on system requirements, so they have to be testable, design models, and executable frameworks. Segment architecture is often a little more concerned with things like reference models and patterns and standards. And, I sometimes say that enterprise architecture kind of moves from an as-is architecture to a to-be architecture for an enterprise. And the way it does that is by spinning out solution architecture projects. Some of those projects may be setting standards and providing guidance for other solution architecture projects, and those are the kind of segment architecture projects. And then some of those projects are actually implementing solutions to business problems, and so that's the solution architecture. I shouldn't say, I got to be careful when I say implementing, because we often think of architects as not being implementers, and that's usually reasonable, but you know, the way that we make changes to an enterprise architecture is by executing a solution architecture project. Solution architecture is going to cover all of the traditional enterprise architecture domains, and by domains we mean sort of types of architecture, and so we often think about business architecture, application architecture, data architecture, and technology architecture. So business architecture is what the business does, what the you know, how do we provide value, how do we capture value. Data architecture reflects the things that are part of the business, and you know, one way to understand when I say reflecting the things that are part of the business is to realize that, especially in transactional systems, but really it applies to all computer systems or enterprise systems, a lot of what we're doing is creating a simulation of the real world, and then taking events in the real world and feeding notifications of those events into the simulation so that the simulation mirrors the real world. That being the case, you know, and why do we do that? Well, because it's easier to ask the simulation questions and to play with the simulation than the real world. You know, it's easier to look up in a ledger book to see, you know, what's my T account for cash on hand currently reading. It's easier to look that up than it is to go to the safety deposit box and count all the cash and coins that I have. Right. So, you know, the simulation is easier to work with than the real world. But that has to be, you know, if that's the case, the simulation has to reflect the real world, which means the data in the simulation has to be an accurate reflection of the real world. And so that's what data architecture is about. You know, how do we model things that are in a system? You know, and those things have to be an accurate model, or else the system is doomed to failure. Application architecture. Well, you know, what do people interact with? They don't interact with data directly, they interact with applications. And so applications are, you know, the sort of human touch points and machine touch points to our data and our system. And so, you know, we have to build applications that people can use that work on the environments that people need, that are available when people need them, etc. That's what application architecture is all about. And both the data architecture and application architecture have to run on something. What do they run on? Well, that's the technology architecture. So I love this. A data architecture focuses on the data architecture. That seems like a real useful definition. But you know, things that are in the system. And technical architecture focuses on what technology gets used. What's the underlying technology? And you know, you also note that the sort of low end of these domains, the technology domains, are you know, liable to be the same across all types of business. Whereas, you know, business architecture is obviously specific to a business. So, you know, technology architecture is more commodity focused, and we're choosing technology that's out there that is appropriate to the applications and data that we need to work with. Solution architecture spans all domains, right? Spans application, technology, business process, whatever. So there you go. Now this is the drawing that I kind of like about you know, moving from a baseline to a target architecture, or from an as-is to a to-be architecture. And you know, so this kind of up here at the top, if I can just sort of point this out. Up here, this is kind of the enterprise architecture idea. So, you know, overall, the enterprise has an architecture, has a set of systems that it uses to fulfill its business goals. And enterprise architecture usually falls out of some dissatisfaction with those systems. Either, I'd like the systems to talk to each other more, or I'd like a system that was designed in this century so I can, buy software updates for it, or something. Or I'd like a system that I could maintain. And so, we think we'd like a different architecture than what we have for whatever reason. And enterprise architecture's job is to move us towards that preferred architecture, move us towards this target architecture. How does it do that? Well, by spinning out some work packages. So spinning out some solution architecture projects. And so every alteration to the baseline architecture is going to be represented as really, addressing a solution. So solution architecture development moves us toward the target architecture. And then, of course, the target architecture is never done because we're always changing due to different business conditions and so on. All right, so architecture. A big aspect of architecture is partitioning a big problem into smaller problems. I have a question. Could you please share some thoughts on the difference between EA and enterprise information model? Yeah, this is where it gets kind of, I think I mentioned that architecture has got a lot of ambiguities. And one of the big ambiguities is questions of terminology and sort of definitions. And one of the big issues is that enterprise architecture as a practice area is relatively new. First mentions of enterprise architecture really start popping up around the kind of late 80s or mid 80s maybe. It'd be kind of early, mid 80s or early 90s. And I'm thinking, Zachman's work at IBM, and I guess there's some idea of enterprise architecture previously, but the whole practice of EA is relatively new. And one of the challenges of that is that there's not a lot of historical context. There's not a lot of what I'd call academic research on enterprise architecture. And so, what's the difference between enterprise architecture and enterprise information model? Well, some people will probably tell you that when we talk about enterprise architecture, we're defining the items that are in the business. And so enterprise information model may be, kind of seen as data architecture that spans the whole enterprise. Other people might tell you, so some people might say that enterprise architecture is the enterprise information model. So others might say, well, enterprise architecture is the practice of, doing this idea of coming up with a functioning business supported by appropriate technology. Anyway, when I think of an enterprise information model, what first pops to mind is the idea that we have a whole lot of sort of transactions and interactions between different parts of the business, and I think of the enterprise information model as how do we model those interactions, and how do we model what information passes between functional divisions when they do transact. And again, that's the the idea of systems are a simulation of something in the real world, and an enterprise system is a simulation of an enterprise. And so, we think about an enterprise information model, we think of how do we pass information between different functional components. And there's also kind of a subtle distinction between an information model and a data model. And I always think the information model generally, you could almost say data in motion and data at rest, because I think of information as kind of summarized and partially processed data that has some meaning, usually formed out of more than one pieces of data. Whereas, data model, you think of how am I modeling the things that exist in the system. When I think of interactions, that's where I start thinking of information. But, definitions may vary. It's rather different from, if you look at more of a more established physical science. And in architecture, enterprise architecture, we often sort of draw references or draw parallels to physical architectures and buildings. And the reason we do that is because the enterprise architecture field is so young that we can't point to academic studies. Whereas if you go to building machines or building buildings, we've got 200 years of experience on what to call things. But yeah, that's a difficult challenge. Good. Yeah, so architecture is about partitioning the whole into parts. And why do we do that? Well, we do that as a way of understanding a system, as a way of understanding the implications, as a way of talking about things and communicating things. I don't know why, because I've been trying to make an attempt over the past 5 or 6 years to learn to play guitar, and I've just kind of recently started. I got in with a jam session group, and it really starts to become apparent that a lot of the sort of things that we do with terminology, and I know this sounds entirely silly that I'm comparing music to enterprise architecture. Just bear with me for a second here, because there's a debate in guitar playing about the benefits of music theory, and the argument is always that the best guitarists couldn't read music. Jimi Hendrix couldn't read music, and what I always point out is that that's fine, but if you're going to step up with a band and you haven't heard the song before, gee, it sure helps if someone says we're in the key of G, and that tells you the basic roots of what you're doing. If somebody says we're playing a 12 bar in G, you have a basic idea of what you're doing, and then you can figure it out from there. And that's kind of what I think of as architecture as a means of communication. See, here's the parallel between music and enterprise architecture. The architecture gives us a way of talking about stuff, okay? So when we break something down, then we can have sort of standardized ways of talking about it. And so then we can communicate. I'm not doing a very good job of communicating, but then we can sort of communicate around the structure. Okay, in the same way that a jam session might start off by saying we're in the key of G, a solution architecture might start off saying, hey, we're doing a 4-tier application here, and now we all kind of know what we're talking about. So we have the general structure of things. Okay, I get a question. Is it common to have a single team doing EA and solution architecture? The answer is yeah, it's not unheard of. Sort of nominally, enterprise architecture is more focused on the entire business and sort of is intended to operate at a higher level of structure. However, most organizations are not really in a position where they want to dedicate a lot of resources to enterprise architecture on its own. So it's quite common to have an architecture group that does a bunch of sort of high-level visioning that we call enterprise architecture work, and then some of them split off and go do a solution. So yeah, it's fairly common to have maybe not a single team, but certainly a lot of crossover between teams and movement among teams between solution architecture and enterprise architecture. Now, usually what happens is the bigger your organization, the more likely you are to have kind of a hard split between enterprise architecture and solution architecture. But to justify that split, I mean, you got to be you got to be major bank level kind of thing, and that's where you normally see it. If you're talking, an organization that's got 10,000 people in it, then maybe you've got a separate enterprise architecture group. And enterprise architecture groups took a real beating in the mid 2000s with the financial crash, because it got real hard to justify sort of huge bet the company projects, and so and architects were kind of required to sing for their supper a little bit and get involved in actually solving problems in implementation. Yeah, so architecture serves as a means of education, communications, and also for system analysis. You know, excuse me. You know, we talk about wanting to predict the behavior of something that is not been built yet. And so that's, you know, our system analysis. And before we actually build something, we'd like to know before we put all the effort into building it, you know, and programming all the subsystems, that we have a reasonable chance of meeting our non-functional requirements, you know, whether that's resiliency or you know, mean time between failure or whatever. And so architecture gives us that sort of starting point. So, you know, any kind of creative process involves synthesis. You know, a loop between analysis and synthesis is the way I think of it. Right? We start off by analyzing the environment and then propose a solution and then analyze that solution to see if it's going to work or to see if it's defensible and it's going to work, and then, you know, maybe we have to synthesize some changes to that or even synthesize a whole new solution. And, you know, what do we analyze? Well, we analyze architecture. You know, if I'm trying to predict, well, you know, what's the mean time between failure, then I can think out the architecture and then ask, well, if this component fails, is that causing a system failure? Or does it just degrade the system? Or does it just make the system more likely to fail later? And, you know, if I'm looking at performance, I can ask, okay, if I have this many transactions occurring at this boundary of the system, how many transactions are occurring at each of the components of the system? And so we can, you know, start to analyze and figure that out. We can't do that without structure, right? We can't do that without some decomposing of the system. Yeah, so solution architecture, you'll find, has all kinds of shareholders or stakeholders. You know, everybody is interested in some aspect of the solution. And, you know, another sort of way to look at things, stakeholders is kind of an important thing. And so stakeholders need to be able to look at an architecture and say, or figure out, well, some of them need to have architectural outputs to do their jobs, you know, to carry on with their designs or whatever. Some of them need to evaluate whether their concerns are met. And so, you know, if you look at the quality assurance staff, well, their goal is to evaluate that there's no defects in the satisfaction of functional requirements. And, you know, they'll use the architecture to help evaluate that. So, you know, stakeholders are going to be just about everyone. What are the deliverables of solution architecture? Well, you know, again, this would kind of like to point out that there's various, I guess, needs or types of stakeholders. And to kind of explain this, I go back to the parallels with building architecture. Okay, if we were laying out an office building, you know, let's just not even make it a whole building, but let's say that you know, my organization has rented a floor in a skyscraper, and you may or may not know this, but if you rent a floor in a skyscraper, there's you know, a hot air channel running up the middle of it, a cold air return channel running down the middle of it, maybe some pipes, and you know, there'll be one feed for power, and that's about it. Apart from that, you're looking at bare concrete and empty glass. And somebody has to come in and you know, figure out where the heating and ventilation ducts go. And somebody has to figure out where the electrical panels go, and you know, I need 150 desks, and so each desk needs 3 outlets. That means I need to have this much electrical current, and you know, that's going to require this many sub panels. Each circuit has to be protected for fire reasons, yada yada. And there's a lot of specialties, and you know, we subdivide the sort of knowledge into different areas. You know, and you know, somebody wants to put a washroom, and we need a cafeteria area, and so there's got to be a sink, and then that area needs ventilation, and then, you know, I want to have a meeting room, and one of the problems with meeting rooms is that sometimes I got 2 people generating hot air in there, and sometimes I got 15 people generating hot air in there, so meeting rooms have particular heating and cooling problems, and you know, so all of this expertise we subdivide between different people, and so the actual design will be split between mechanical engineers and electrical engineers, and heating, ventilation, and air conditioning engineers, and communications engineers, because we're going to network everything, all under the sort of overall guidance of an architect who is probably basing a lot of their decisions on cooperation with an interior designer or an office designer, a layout designer. Well, that's a whole bunch of different stakeholders. Okay, some of the stakeholders need the floor plan to go ahead and plan out the rest of their jobs. Some of those stakeholders need to evaluate the proposed build. You know, the fire safety officer, the fire marshal, needs to be able to take a look at the floor plan and the electrical plans and the fire alarm plan and say, okay, yeah, this is going to be safe. If there is a fire, then, you know, there's enough doorways that people can get out, and you know, we're going to set off alarms so that we can get help, etc. So some stakeholders are needing architectural deliverables or outputs in order to continue on doing their jobs. And some stakeholders need architectural outputs in order to evaluate whether those stakeholder concerns have been met, or whether that stakeholder's concerns have been met. We do this with deliverables, you know, so it's you know, it's good to define what exact deliverables we need and what, in fact, artifacts do we need. So we talk about artifacts being the result of doing work, the things left behind. What artifacts do we need to have? And so typical solution architectural deliverables would be things like architecture use cases and scenarios. What's that doing? Well, that's helping to drive the design. So that's going to be used really by solution architects and application architects. Requirement specifications may be used by people involved in testing, also people involved in sponsoring the system to make sure the requirements are in there. Architecture and design patterns might be guidance for implementers. Standards or references to technical standards that guide long-term interoperability or even guide sort of general design approaches. Guidelines and best practices. We talk about guiding. Well, you know, that's the architect has to kind of convey his or her vision and what's important in the design, because you can't delegate, or well, you have to delegate the detail work, but it's not practical to bring all of the detailed decision making back up to the architect or back up to the architecture level. So we need to provide guidance and best practices and principles and policies and procedures on how we're going to do things and how we're going to make decisions. We'll need an architecture description document. And, you know, usually for convenience, we'll subdivide that into the traditional architecture domains of business, application, data, and technology. We need to, you know, visualize how information moves in the system, and that's typically system process flows. We may need to, you know, realize that we're going to make a lot of decisions that are open to being questioned, you know, that we may have to defend, and that the same questions may come up in a year from now. And so we find it really useful to create an architecture decision document, or you know, a set of architecture decision documents explaining and justifying the decisions that we made, so that you know, if ever asked to revisit those decisions, then we can simply say, well, here's why we decided what we did, and that gives a lot more weight to that initial decision making. Yep. So, you know, that's deliverables and artifacts that we communicate. And if you were to take the full, I think this ends up being a 4 or 5 day course, we go kind of deeply into the idea of views and viewpoints and selecting architectural artifacts. And, you know, a short version of that, start with who are the stakeholders, identify their concerns, quantify the stakeholders or classify the stakeholders based on their level of interest and level of influence or power, and then design a set of artifacts or select a set of artifacts that does the best possible job of providing each stakeholder what they need. But sort of early on, I mentioned this thing about synthesis and analysis loops, and we've got to come up with an architecture. We have to sort of set down the core architecture so that details can be filled out within it. And in order to do that, we have to be able to identify or have some feeling for what aspects of the system are what we'd call architecturally significant. Okay. And what architecturally significant, by definition, it's kind of a circular definition, but it does kind of make sense. We're working with models that are complete representations of the system. In other words, a very high-level model. Architects focused on the architecturally significant elements. In other words, the things in it that are, important enough that they alter, that they're visible at this high-level model. So an architecturally significant element has a wide impact on the structure of the system and on its performance, robustness, evolvability, etc. What's that mean? Well, if I am designing a system which is going to have 100 users, okay, the architecture that I design may be quite significantly different if those 100 users are all in one floor of the same office building, or if they are spread out, 1 per state or 2 per state in the continental U.S. So that's an architecturally significant element. So architecturally significant use cases, architecturally significant requirements, architecturally significant constraints are those things that have an impact at the architectural level. So things like major classes, especially the ones that model major business entities, mechanisms that give behavior to the classes, like persistency mechanisms and communications mechanisms, patterns and frameworks, layers and subsystems, interfaces, and major processes. Okay. Okay. Yeah, I just have someone who's got to leave us at 3 o'clock. So thank you for coming. I do enjoy having a look at the material, and the audio is going to be out there. All right. So yeah, architectural significant elements are the things that are kind of big enough to impact the architecture. And so that idea comes up at every level of architecture. In application architecture, we talk about architecturally significant use cases. Those are the 80% or 20% of the use cases that are going to actually determine what the application architecture is. So architectural significant elements are things that are big. Architectural views are kind of like slices cut through the various models, illuminating only the important significant elements of the models. And again, to kind of, illuminate what a view is, and what difference between a model and a view. If you think of, go back to my office layout example, there'll be different drawings generated for where the pipes and the heating ducts go versus where the electrical conduits go. And the reason for that is that, if you put all the detail of the electrical conducts on top of the floor plan, I wouldn't be able to look at it and say, I don't have enough desks for this group here, or this group works with this group and they need to talk to each other. But as far as actually designing the system, someone's going to document that. And so the architectural views are kind of a view of the entire system, but only with those elements on it that are important to a particular set of stakeholders. And so, the mechanical designers have, their mechanical view where they're showing ducts, and the electrical designers have an electrical view where they're showing where the panels are located and where the conduits are. How do they not conflict? Well, that's where the architect comes in, because the architect will probably say, here's the policies. We're going to run ducts down the middle of the floor, and conduits are offset by 36 inches to the right of the heating duct, right? Or we're going to run heating ducts, 6 inches from the beams, and conduits can go 3 inches from the beams. But the architect sets down the guidelines on how the other participants can do the work. Okay, so I don't know if we can really have a group discussion with 118 people, but yeah, think about what architecture roles are defined in your organization. Do you have enterprise architect, solution architect, application architect? I've seen integration architect. I've seen software architect. There's a lot of possibilities. Okay. Some resources you might want to look into. Software Engineering Institute at Carnegie Mellon has been a big researcher into areas of architecture, and in particular, commercial off-the-shelf architecture, product line architecture, quality attributes. The idea of benchmarking that we often use, or CMMI, comes out of Carnegie Mellon, and so that's a useful resource. Software Engineering Book of Knowledge, based on the IEEE standards, IEEE 1471 and assorted standards, talks about software requirements, design, construction, testing, maintenance, etc. OpenUP, I haven't heard a lot of this in the past few years, but lean unified process that applies iterative and incremental approaches, kind of an open software development on rational unified process. And I'll just point out, even if you're not sort of Microsoft focused in your software architecture, the Microsoft MSDN, or I think they've changed the name, it's like Microsoft Archives now or something, they actually have a lot of good information on software architecture, so well worth skimming through MSDN. But I won't worry about that. So, enterprise and solution are both systems. We have a lot of sort of commonality between practices. Enterprise target architecture guides and constrains the solution architecture. We didn't really talk about the enterprise architecture roadmap, but insofar as enterprise architecture spins out solution architecture projects, there's normally a plan of what order those projects come in. That's the roadmap. And then solution delivery updates the enterprise architecture baseline. So the solution is what moves us forward toward our to-be architecture. Okay. Pardon me, I'm just pausing to have a drink of water. I'll be right with you. Okay, so core solution architecture methods. Yeah, here's one that I really like, which is the idea of a shared vision, where I've actually seen it said or stated as a shared hallucination, where we say, architecture is a team effort. It's a collaborative kind of affair. And in order to have a team effort where we are sort of collectively creating something, and that we have to have kind of a shared vision of what that is. In order to discuss the potential thing that we're creating, we have to be able to convey, an idea of something that does not yet exist. So the shared vision is a critical success factor. And so in order to discuss a shared vision, we document a shared vision. And then we can talk about, is it going to work, or is it worth building, and is it going to evolve the way we want to? So here's an example shared vision where we have some areas around business rules, OLTP, we got business intelligence, we got a security layer, whatever. So in discussing this shared vision, someone who is interested in, can I make sure that my stakeholders are able to call up and see if they owe any taxes? Yeah, I can look at, here's my taxpayer has a whole bunch of options as to how to talk to us, and we've got a security layer that makes sure that I can't find out about someone else's taxes when I shouldn't be allowed to, etc. So, we can talk about the shared vision even before we build it, even before we have something that we can put our fingers on. First step in designing a software solution is to draw a boundary around the solution, and something that I learned through an interesting little demonstration that we used to do when we first started teaching object-oriented analysis and design, which is kind of par for the course now. So we actually don't do a lot of OOAD education these days. But in the early days, we used to have to explain object-oriented analysis and design. And we would go through an exercise in the class about, designing a system for a video store. And, yeah, I know, what's a video store, Grandpa? That's a place where, it used to be that you wanted to watch a movie. Well, after, there was a time when you actually had to go to a theater and watch a movie, and then there was a time when you could go to the video store and get this little thing called a video cassette that you could load into a video cassette player and watch it. So, and of course, now it all comes down the pipe into our homes. But we used to do this exercise on implementing a video store system, and it was very interesting. I noticed that we'd have people go through, what's a video and what's a rental, and go through a set of use cases that described a customer coming in and looking for a movie and wanting to ask, do you have anything that was directed by Martin Scorsese, and then, selecting a movie or selecting half a dozen movies and then asking for the movie at the front, and every movie had a different return date and so on, and the cost for the movie. And we'd go through all this, and the funny thing that I found was that in any exercise like that, every design that's created, every analysis that's done is going to be a little bit different, but I frequently saw a couple of themes. One of which was the complexity of the system really changed a lot depending on where you drew the boundary around the system. If I said the customer asks if a movie is in stock, okay, then that's kind of putting the video store clerk as inside the boundary of the system, so that they're part of the system. And that leads to a certain level of complexity and a certain interaction with the system across that boundary. And if, on the other hand, the video store clerk was viewed as being outside the system and people were designing inside the boundary, that was a whole other level of complexity. And it was kind of interesting. So drawing the boundary, where you drew that boundary, did it include the sales clerk or not, actually had a significant impact on the design of the system. And so boundaries are kind of important. So, first step in defining a software solution is to understand the boundaries of the solution. Without the boundaries, the solution's a moving target and will quite often end up far more complex than it needs to be. So, the boundary of a system separates the internal components from the external components, and best defined by understanding the overall intent, the external events that trigger the solution's functionality, the external processes that the solution depends on, and sort of what's the interaction at the boundary. And that leads us to the idea of a well-defined interface. So well-defined interfaces are important, because it's been an architectural principle for a lot of styles. But think about, what an interface means. The idea that back in the mid-1800s, when railways started to be built, the first railways were all sort of proprietary implementations, and so railways started in England with the Stephenson's rocket, and the railway that went from London to Brighton had one width of track and one kind of connection between the engine and the cars. And the railway that went from London to Brighton was built by somebody else and had a completely different width of track and a completely different connection. And one of the great sort of enablers, really, stopped in a few years ago. I was on a trip down to Florida with my kids, and I always figure if we're going to Disney World, then if I'm going to Disney World, then the payoff for the kids or the cost to the kids is they're going to have to stop at a museum and learn a few things. So on the way down to Florida, I stopped in Washington, D.C., and we spent a better part of a day at the Museum of American History. And historians trace a lot of the U.S.'s economic development to the adoption of a standard interface for railway cars. It sounds kind of silly, but the fact that you have the wheels of a rail car are 4 foot 6 inches apart, or whatever it is. I forget what exactly it is. And the hitch is a certain dimension, and the brake lines have a certain standardized connector. And that enables a lot of things. That enables the idea that one small vendor of oranges in Florida can load up a car filled with oranges and have that integrated with a train that's going out west to California. And that same train, that same engine can serve can transport oranges in the fall and transport motor parts in the winter. And so the standardized interface enables a lot of development. And similarly with enterprise architecture, having a well-defined interface makes it easy to design around it, and also enables a lot of interconnectivity and common usages. So well-defined interface is a common theory of object-oriented programming, structured analysis and design, message-based architecture. Everything depends on a well-defined interface. So here's, for example, a context diagram, and I'm not sure where this comes from. It's I think out of the HL7 reference documentation, but here's a healthcare delivery organization, and this organization has interfaces with other entities, and the idea is by decomposing this overall system into a number of actors or participants, and then putting a boundary around our healthcare delivery organization in the middle, then we can make sure that we have documented the interface to all of our sort of counterparties. Right? And we get to the idea of interface specifications and documenting the information that crosses the boundaries. So we identify the external interfaces. Interface specifications are critical to define interface frequency, protocols, expected volume. They have to specify data elements, and not just business meaning, but eventually we have to specify formats. And so we can also have definitions at various levels of detail. But certainly at some point we have to specify formats and nitty-gritty representations. So we got to specify data elements, have to specify acknowledgement and error handling mechanisms. How do we make sure that information has crossed the boundary? Do we have to? Do we have to have an acknowledgement? What happens when the connection is broken? Is there some way of detecting when the connection is broken, etc.? And all these interfaces have to be reviewed and approved by all the impacted stakeholders. A system gets decomposed into subsystems. Okay, so subsystem is a small version of a system, a small component of a system. Bigger than a component, smaller than a system. Subsystem is a collection of classes, interfaces, and components that make up a development package. So defined so they can be assigned to different development teams, and this is kind of critical. So we get parallelism in development. Just reading out a comment or a question. Someone had said they work in the enterprise architecture services. Has the enterprise architects, solution architects, data architects, and data modelers all under one umbrella? Yeah, interesting. That makes a lot of sense. Now, having said that, other organizations might differ. Some organizations need rivalries between departments, and some don't. That's interesting observation. Thank you for that. Yeah, so subsystems are pieces of a system, should have high cohesion and low coupling. We're getting into kind of architect speak. What do we mean by that? Cohesion is the feature that says every piece of a subsystem is working on the same thing. So the subsystem kind of has a unified purpose. And low coupling is the trait of not being all that dependent on the implementation of a different subsystem. So, you know, really it boils down to I can change one subsystem or change the internals of a subsystem without it impacting anything else. And if I can manage high cohesion and low coupling, that tends to lead towards good maintainability. So that I have a lesser chance of breaking things when I go to fix something else. Okay. So subsystems describe the design and build time, structure, interfaces, and dependencies. And so, you know, you can build subsystem context diagrams. And again, this is really just, you know, within our system boundary, what subsystems do I have and how do they interrelate to each other? A common approach to decomposing or decomposition of a system into subsystems is layering. Now, layering is kind of a conscious thing. It says basically, and yeah, I'm just going to bring up a pen and do a little freehand drawing here. So we have a system. Okay, a system has components in it. And I'll draw out 1, 2, 3, 4, maybe 5 components. Okay. And these components have interconnections. Now, if we just say it's okay for components to talk to other components directly, what we will have is, you know, this component maybe ends up with a connection to that component and that component and this component and this component. And then this component already has a connection with that one, but needs a connection to this one and to that one and then to this one. And this component is going to need a connection to this one and then to this one. And yeah, we already have a connection to that one. And then this one has a component or a connection to this component. And the net result is that we end up with a lot of connections between components. The actual numbers n times n minus 1 over 2. Okay, and if we work that out, so if I got 5 components, that suggests 5 times 4 is 20, that I have a possibility of 10 connections. I get 6 components. Whoops. Uh-oh. Back to my pen. If I have 6 components, that says 6 times 5 is 30 over 2. I get a possibility of 15 connections. Okay, if I had 10 components, I'd have 10 times 9, 90 over 2 is 45 possible connections. It doesn't take long to end up with kind of a real explosion of connection points. And connection points are dependencies. So what that means is that, you know, if I change one of these 10 components, there's a chance I might have to change 45 other 45 connections. A pretty good chance that I have, 9 other components that need to change. So that's kind of a bad thing for maintainability. The idea of layering is to say we're going to apply some constraints. We're going to say I'm going to divide my components into layers, and my rule is going to be that a component only talks to components that are in a lower layer, or really the next lower layer. And not too many of those, for some definition of not too many. Okay, so this component then may have a connection to that component and that component. This one maybe has a connection to that component. This one has a connection to that component. So at every layer we are saying, each component only talks to components in a lower layer, and ideally only one or two of those. And the net result, here I designed a setup with 5 components, and instead of the 10 connections that are theoretically possible, I end up with 1, 2, 3, 4 connections. Okay, and that scales actually a little more linearly. And the idea with layering is to apply these constraints so as to avoid, an explosion of complexity. And that's kind of another theme of architecture I always like to point out, is that we are continually in a fight with complexity and emergent complexity, and complexity which may emerge as time goes on and as we have more implementations. And so layering is an approach or a technique that we use to sort of impose some constraints on the connectivity of objects, such that we control that complexity which would otherwise emerge. Okay. Right. So here's an example, subsystems with layers, and sometimes people organize layers in different ways. With SOA, we would often organize layers into orchestration layer, business services layer, application services layer. We sometimes organize, your traditional 3 or 4 tier applications. We would think in terms of user interface layer, business logic layer, and storage layer, right? And a number of different possibilities. So here's a case where I have a business domain layer and a foundation layer. So I have a business domain layer that, is working with settlements and customers and mortgages. And then my class library has date, time, XML parser, and database. And the idea is that, we may be able to replace layers. Certainly we have limited connectivity between layers. Components are modular and easily replaceable things in our system. They provide services through a set of interfaces that are well defined, and we know that the internal sort of implementation of a component may be different from what the externals see. It can be made up of several classes, interfaces, and resources. They depend on a component framework to provide startup and communication. Components may encapsulate both state and behavior, and components are describing the runtime system. So components are what we build out of. And so components really, they have an analog, or they have a representation in some representation of the build. So how do we go about decomposing a system? Right, the architect is responsible for decomposing the system. Well, kind of in the bigger picture, the architect's responsible for coming up with a proposed architecture that meets our requirements, those functional and non-functional requirements. And so, we start with one big problem, one big set of functional requirements, and we want to decompose that system into a structure of components and subsystems that can meet the functional and non-functional requirements. So we do that typically by applying some form of architectural style or architectural pattern. Because what we found is that there's common ways of doing things, right? For certain types of systems, we find messaging works well, so there's a messaging pattern. Certain types of systems, that are implementing business processes, well, orchestration patterns work well. And so we decompose the system quite often under the guidance of an architectural, style or pattern. So the architectural style or pattern chosen typically specifies how we decompose responsibilities. Okay, and so there's a number of general architecture patterns that can give us guidance on general partitioning strategies. Encapsulated implementing, master-slave pattern, have object plus protocol, and there's a whole bunch of patterns. Now, patterns are maybe a little bit overrated. The patterns are kind of like music theory, in that there's no rule that says that you should have a 1-4-5 progression, but if you know enough music theory, you can point out that if you start from a 1-4-2-4 progression and then throw in some frills, then you've got a pop song. That's kind of what patterns are. They're more about being able to talk about architecture, so we refactor to patterns. We shouldn't really use patterns as a design catalog. But common patterns that we use, model view controller has the solution composed of model components, view components, and controller components. SOA, we divide into orchestration layers, so processes and sub-processes, and then business services, and then application services. Master-slave pattern, responsibilities are allocated between the controlling master component and agent components that handle each transaction. Pipe and filter, where responsibilities are allocated based on sequential sequence of work, and then the sequence of work can be allocated to different work units. Three-layer pattern, or three-tier, five-tier, N-tier pattern, real common architectural pattern. Says we got user interface, business logic, and data access. And then each layer may have multiple components. So the UI layer has components by UI object and event. The application logic layer is based on domain objects, and data access layer is based on the data model. And you can kind of divide. Here's an example of a service-oriented architecture framework where we've got business processes running at the top, and those business processes make use of business services, and those business services make use of application services. The idea of requirements allocation is kind of an interesting one that to be totally open with you, I haven't seen it used a whole lot, but it's a good idea. I've had some good luck with it when I've used it. But the idea is that what's one of our main concerns is, are we satisfying our requirements? Well, the suggestion of requirements allocation is that something we might want to do is actually document what component is responsible for satisfying what requirements. So regardless of how the system's partitioned, requirements have to be allocated to the defined partitions, and requirements can be allocated to software components, hardware components, etc. But if we practice or make it a habit to kind of define what requirement is implemented by what components, then that gives us a way of sort of double checking that we are implementing the requirements. Okay, and I'm not going to bother with interactivity that much. Yeah, and all this has some impact on configuration management and solution design. So the so-called configuration management or source code management tends to follow along with how we subdivide the components in the system. Right. Same with release management. The components or subsystems are often candidates for independent release or management of independent releases. Testing, clearly it's a sensible breakdown to test things in a component-oriented fashion. So you can test from the outside, from the system boundary into the components, or you can test from the component level on up or on out to the system boundaries. Right. Work pattern and skill set, it often breaks down into prototypes, interface development, persistence design, etc. But the skills required, and hence the personnel allocations and the people needs of a given area of the architecture are quite often different in between the tiers or in between different areas. So it's real common to see that we talk about back-end programming versus GUI programming or front-end programming, and so that may have implications in works pattern. Obviously, work and build dependencies. How do we build things, and dividing things into separate areas helps us to structure the overall task of building it. Increment and sprint planning can be applied at any level of the architecture. Okay. Sizing implications. Well, if we have a structure and I've decomposed the structure, then I can start asking questions about, well, how long is it going to take me to develop this? Then I can look at, well, how many interfaces do I have, and how many operations are on each interface, and so on. And so, the decomposition takes us a long way, or assists a lot in evaluating and sort of predicting the resource usage. Okay. So architecture required to meet the functional requirements is important. That also will have some bearing on the development architecture and the operations architecture. So development operations is, what architecture is required to support development, test, and deployment, and then operations architecture is, what's the process of software and hardware required to support the monitoring and the operations of the solution. And so, think about the architectural components that are needed for testing, data conversion, data quality verification, etc. Typical development architecture, and it's kind of also trending towards DevOps. You tend to have requirements management. You tend to have source code management. Tend to have a build tool or test automation tool, or as the case may be. Same with operations architecture. We need to monitor operations, but all this can be built around your solution architecture as well. So, summary, we talked a little bit about solution architecture methods, primarily around the idea of a shared vision and also around the idea of decomposing and thinking in terms of abstractions and thinking in terms of components in the system and how the system components and modules and subsystems interact. And I really want to focus in on the idea of well-defined interfaces there. And I joke about architecture being about drawing boxes, and unfortunately it's not really that much of a joke, because a big part of what we need to do is draw boundaries around the system as a whole, and then subdivide those boundaries internally into subsystems, and then subdivide again into components. And the organization of those components is what makes up our architecture. And the fact that we have organized as components allows us to ignore the details of the components. Oh, I got a question. How do you harvest value from this work role decomposing and documentation? Yeah, that's a good question. How do I harvest value? I think I can tell you what the value is. The value is that we end up with an intentional architecture in the final product rather than an accidental architecture. And when we have an intentional architecture, we have a much better chance of the architecture being maintainable and extensible and evolvable. Now, how do I harvest value from that? In other words, if I'm thinking of harvesting value, is how do I justify that I have a group of architects with salaries and office expenses to be paid, and how do I build the development groups? Quite often, you'll see an architecture tax applied on development, or just a plain requirement that architecture has to sign off on overall development architecture. I mean, what the value is, identifying the value is easy. The identifying the value is just that if we do some architecture up front, the development will be faster and more parallelizable and more maintainable. So our future costs will be reduced. But how do I harvest that? Well, it's real hard to bill for infrastructure. It's kind of like the only way if you have to figure out how to pay for a highway. You can think about paying tolls, or charging tolls forever. That's not a real popular option, but that's kind of one of the reasons why unless you're a radical libertarian, you figure that building roads is kind of what we pay taxes for. That's kind of the I'm slipping into politics here, which is a dangerous area, but that's we kind of have to accept the cost of doing architecture as just something that has to be done. Otherwise, we have just total anarchy. And if you think back to how architecture groups started up and how enterprise architecture ends up, and of course we see this a lot in training, because people are often coming to us when they've sort of identified that, gee whiz, we ought to have enterprise architecture, and or even software architecture. And usually it comes from unhappiness with the fact that you have a whole bunch of systems that don't talk to each other, and that you can't fix because if you fix one thing, you break 5 other things, or that we don't have data exchange, so we have errors and we have duplication of efforts. So that's kind of why people set up architecture groups in the first place, is to avoid that kind of downfall. So that avoidance of unpleasant results. So how do you pay for that? Usually it happens that people just have a problem they want solved. Anyhow. Okay. Yeah, so that's a little introduction to sort of core ideas, and the big one again I always like to get at is decomposition. The idea of taking a big problem and cutting it into pieces. And how do we do that? Well, we're guided by solution architecture patterns, solution architecture styles, and then we come up with a proposed architecture, a candidate architecture, if you want to call it that. And then we have to evaluate that candidate architecture to see if we think it will meet our goals. And then we may have to go back and do another round on synthesis and analysis. Okay, so yeah, we'll take a look in a minute at building modern applications, and yeah, I think we should be able to cover most of it. It's kind of a long chapter, but yeah, I think we got a better part of an hour. I just need about a minute and a half to just have a drink of water, and so hold tight. I'll be right back. Yeah, the one problem with these webinars is in a large group like this, it's kind of hard to have interactivity, and the secret, the dirty little secret of interactivity and having discussions and labs and so on is that it gives the instructor a chance to stop talking and catch your breath for a little bit. If we don't have that, we're going to work around it. We'll have to edit that out of the recording. Anyway, yeah, so building modern applications. All right. This is, because we're talking about solutions architecture. In the end, solutions architecture also encompasses applications. And even when we talk about, an application, we're never really talking about just one application. We're talking about usually a suite of applications that work together. And, so it's good to have a look at kind of what's the state of the art on kind of, I won't say low-level software architecture or solution architecture, but kind of, mid-level, how do we put stuff together that people use these days? So, in the past, I don't know, 5 or 6 years, really, it's been never-ending over the past 10 or 15 years. A lot of things have changed. New methodologies, new tools, new approaches for designing and building applications. We have seen a great acceleration of the sort of delivery cycle times, to the point where a lot of organizations are now saying, and with some decent evidence, that they're delivering solutions on a daily basis and delivering updates and bug fixes on a daily basis. We've really moved away from having a simple application that we'll deliver a new revision every year and a half, to things like continuous improvement, continuous delivery, continuous integration. And the nature of applications has changed. The big thing that has hit us is things like mobile applications and the RESTful API approaches that go along with that, and the associated security issues, and also aspects around how do we handle back-end data, the idea of deploying to the cloud where we don't have dedicated resources or dedicated hardware resources in most cases now. That's even extending into network structures or network infrastructure. So, we now talk about networking as a service or software-defined networking, where, we can define gateways and firewalls and local area network segments on the fly. All this leads to new ways of thinking about architecture. So, it's kind of good to step back every now and then and see what the current practices are. And so solution architects often find this area kind of useful. First area that's really changed things a lot is the idea of Web 2.0, and Web 2.0 means a lot of things, and even now the term is starting to look a little stale in itself. But basically, it says that the World Wide Web, and in particular the Hypertext Transfer Protocol, is not about filling out a form and retrieving a web page from it. Users are not passive consumers of static content. We now have sort of higher level interactions. Users generate content, and devices are sending content and sending requests and sending, in fact, application information across the web. Which leads us into the idea of rich internet client applications, and the idea of having JavaScript running in a browser has been out there. JavaScript was built into the first Netscape browsers back in 1995 or so. But most of us sort of casually ignored JavaScript or treated it as a quick and dirty scripting language that we can do a little bit of client-side validation in until Google popped up and showed us Gmail. And, it became apparent that, yes, there was a lot of value in putting the user interface entirely into the browser and using the browser as the complete computing environment that it is. Limited in some ways, but, complete in that it can process input, output, and interact with the user all on its own. Limited in that, browsers typically can't do things like read and write files to disk. But it is a complete computing environment, and we are now seeing, the normal way of delivering a web-based application is to think of the user interface as an application that happens to run in the browser, and it communicates with its proximal back end, or what we sometimes call the back end for front end, through a service interface or a RESTful API interface, a programming interface. So browser vendors now have robust implementations of JavaScript. JavaScript turns out to actually be a pretty powerful language. It isn't the quick and dirty scripting language that we all thought. If you look into the history of it, JavaScript is actually based on the implementation of the Scheme language, which is a version of Lisp, or a dialect of Lisp. And as a result, JavaScript has some really neat features to it, actually, and has some neat extensibility and very high-level features in what looks like a simple language. So we have a complex computing environment in the browser, and it's getting faster for two reasons. Number one, your personal computer, well, heck, your phone has more computing power than ever flew on every space shuttle that was built. And, computing power is regularly 64-bit multi-core CPUs and lots of RAM. So we can treat the browser environment as a rich environment, basically. Single-page applications are pretty much common practice now, and pick an implementation area. A lot of people got on board with AngularJS. AngularJS has morphed into what's now called Angular, slightly different language, slightly different architecture, but both sort of based on the idea of treating the user interface as an application that's running inside the browser. So single-page applications use some HTML templates, but mostly JavaScript and libraries that are running in the browser, so that the user really is interacting with an application. It's just that to get anything done, that application has to interact with a back-end service. And this is kind of maybe a little deep, but AngularJS uses something called two-way data binding, and really, because we're talking about architecture, I'm just going to point out that you can do some serious programming inside AngularJS. The concept of it is I have an HTML template, and in that template, maybe I have an input text block. So I'll have an input element, input name equals ABC, and I'll put in value equals, and then connect that input to a variable that's inside JavaScript. And again, if I have a button, I'll connect that button to an event handler so that when the user clicks on a button, we get to run some JavaScript code. And then that JavaScript code can just use the data that has already been set up. And so, that's just a powerful mechanism that, sort of similar to model view controller development in Java, Swing library, or in ActiveX or Visual Basic, but very much in the browser. There's a few other client-side frameworks. EXTJS has a full GUI component library, also a charting library. AngularJS doesn't include components, although there are add-on libraries that do have components. React comes out of Facebook, seems to have a lower learning curve. Some people say it's higher performance. There has been some controversy over the licensing model of React in the past year or two. Backbone.js is a lightweight MVC framework created after AngularJS, positions itself as a lean alternative to heavyweight MVC frameworks. And then Angular 2.0, which is now just called Angular because it's also Angular 4 and Angular 5. Anyway. So, this is the idea of rich client and thin server. So the rich internet application design model says we'll have rich client, thin server type of application architecture where the application communicates with the application server via some communications, either through HTTP connections or WebSocket. WebSocket is another newish protocol which is now widely supported by the various libraries and servers, although we haven't seen a huge uptake of it in most enterprises yet. But what WebSocket lets you do is keep a connection open and have a connection, two-way connection open between the browser and a back-end server. What this does, the big import of it is that traditional HTTP is a request-response protocol. The browser sends a request and gets a response. Well, when does the browser send a request? Typically as a result of the user doing something. And that, might make a lot of sense. Typically, a user finishes filling out a form and says, please process this. The browser does a request, but that doesn't allow for kind of asynchronous updates. If I want to know when my commuter train is going to be entering the station, and I want my phone to buzz in my pocket so that I can decide to, head out to the platform. That's an asynchronous call. It's responding to an event that is happening on the server, and that information is being conveyed to the client. And that's not possible with traditional HTTP, not directly. Whereas WebSocket says we can keep a connection open and actually just send a message down it at the appropriate time. So WebSockets are not restricted also by the same origin script policy So you can hit different servers with a WebSocket. Essentially, servers' responsibilities stay in the traditional scope minus dynamic content generation. So content generation to client browsers reduces load on the servers, right? So we make basically we download one application to the browser, and then we're just sending data, and that obviously reduces the work on the server. Mobile platforms. Yeah, we'll mention BlackBerry and Windows Mobile. I think, well, as I look around my office, I do have a BlackBerry Playbook tablet hiding over in the corner that I think it's turned on. It still shows up on the network, but I haven't looked at it in probably been a year and a half. And yes, there is a BlackBerry Z10 or Z10 phone sitting on my workbench or my bookshelf. Hey, don't you be hating on the Playbook. It was actually a very slick interface. I switched over to an iPhone probably about 2 years ago from my Z10, and I still have ingrained that, if I want to change applications, I just flick my thumb upwards and wonder why nothing happens on the iPhone. Anyhow, funny thing about the Playbook, I'll just digress a little bit. It's maybe not obvious, but when BlackBerry decided that they wanted to, sort of improve on the operating system, what they did was they went out and they bought a company called Qnix, or Quantum Software. Well, it was originally Quantum Software, then it was sold to Harman, which is Harman Kardon Audio. And this is all whacked out. The intricacies of it are BlackBerry was created in Waterloo. Waterloo was also the home of the Qnix operating system way back in the day, and one of the directors that was on BlackBerry's board was a fellow named Jim Estel, who owned a company called EMJ Data Systems, which was originally one of the early vendors of Qnix. How do I know that? Because I worked for Jim back in 1985 and did product support on Qnix. And so when they looked around and said we need a new operating system, they came across Qnix. And Qnix is actually a really cool operating system. It's an early microkernel, microservices-based operating system. So early Unix-based. There's my first exposure to Unix-like operating systems. Well, my first exposure was Unix on a PDP-11, but then worked with Qnix after that. But yeah, the Playbook was actually quite a nice tablet, and it had one of the best, earliest implementations of HTML5. Yeah, cars use Qnix. I think it's the Audi entertainment system is running on Qnix, and one of the founders of Qnix, Dan Hodges, he left recently. Was it Dan Hodges? No, it was Dan Dodge, I think it was. There was two of them. There was Dan Hodges and Dan Dodge. And one of them, unfortunately, died of brain cancer about 5 years ago. I think that was Dan Hodges. So Dan Dodge was still with Qnix after a while. But yeah, it's used in cars. That's before BlackBerry bought them. They were owned by Harman, which is Harman Kardon Audio. But Harman is also one of the big vendors of original equipment audio systems for cars and entertainment systems for cars. So yeah, a lot of, if you have an Audi or a Volkswagen, the entertainment system is Qnix. But yeah, really slick operating system. I was always disappointed they could have done so much more with it than what they did in the phone. And there's well, nuclear power systems operate on Qnix. If you have one of those highways, there's a highway that runs through the Toronto area where I live, called the 407 highway. And if you don't have a transponder box, there's a set of cameras that snap your license plate, and that whole network of transponders and cameras is running on Qnix. So actually the same operating system that was in the Playbook or the phones. Anyhow, so yeah, mobile platforms. The ones that are left are really Android and iOS. And in terms of, I guess, mind share, probably iOS is best. I think in terms of, or not best, but biggest, in terms of actual deployed devices, last I looked, Android had the edge on it. Windows Mobile, I think even Steve Ballmer's given up on Windows Mobile, and similarly with BlackBerry. BlackBerry switched over to Android operating systems in the phones that they license the name on these days. Anyhow, so the thing with these mobile platforms that you need to realize is that they're high performance user interface. There's actually quite a lot of performance in there. I mean, phones are typically quad core, multi-gigabyte memory, and slick power management. They're often constrained in how they can talk to backends, though. Really, as a matter of the mobile network limitations. The mobile network vendors, thinking AT&T and Rogers and Sprint and so on, typically will limit the communications to being hypertext transfer protocol. Nowadays, they'll often allow for WebSockets as well. And so that kind of limits the interaction style that we can have, which has led us into RESTful API. Now, that's kind of nice, actually, in that if we limit ourselves to, or if we constrain ourselves to RESTful API, well, for all the reasons that Roy Fielding laid out in his dissertation, REST works well on the internet. But also, it allows us to use the same backend for all the mobile platforms and all of the sort of rich user interface platforms. So, if you have a front-end app that is using Angular, no reason the backend for front-end cannot be the same between the Angular app and the BlackBerry and the iOS app and the Android app. Okay. So they're basically mobile operating systems that let users run applications on handheld devices. Now, those applications, we have some possibilities, and for a device, and whether it's a tablet or a phone or whatever, you can have a native application, by which we mean an app that's implemented in whatever the native language is. So that could be on an Apple device. Could be Objective-C or Swift, or on an Android device, would typically be the dialect of Java, or in later devices, actual Java. There's also a possibility called hybrid mobile applications that is kind of interesting too. So native mobile apps are specific to a given platform, whether that's Windows Mobile or iOS or Android or whatever, coded in the platform-specific programming language. And that will often be the best performance and usability. Having said that, the performance, most applications don't really see that much unless you're doing something that is particularly processor intensive. The big difference with a native app is full access to the system devices and sensors, which is sometimes not available in a web type application. So, direct access to accelerometer and things like the camera and the video system and the sound system and the file system. Often they have the ability to work without an internet connection. Now, in fairness, HTML5 does include some caching capabilities, so and cache control capabilities and cache manifest and so on. So you can actually have offline apps with HTML5 as well. But a native app is sort of by definition available offline. And then they'll be available in the target mobile platforms app store, may or may not be available for what we call side loading apart from the app store. Mobile web apps are applications which are just standard web technology. They happen to be formatted for the screen, appropriate to the device. And so that would be an app that we are deploying on a standard web server. You hit it at a URL, and it's just the rendering is designed for mobile browsers. So we might use, bigger fonts or bigger buttons relatively, and libraries that are geared towards, gestures instead of clicks. So page design takes into account target device's screen. Typically, a mobile app or a mobile web app will have limited access to the underlying system devices. You know, a browser, you know, if we're running basically an app in the browser, it doesn't have access to the camera. And you know, has limited access to things like the accelerometer, you know, what's the orientation of the device. Now you can use things like the location. So there's a geolocation API built into HTML5 that lets us, you know, figure out where we are using the GPS. But you know, we're not going to have intimate access. It's very difficult to implement a sound playing application in pure JavaScript and HTML5. The kind of in the middle of those would be hybrid mobile apps. So the advantage of the mobile web app is that it's possible to do one web app that can work on all mobile platforms, which is kind of convenient. You know, given that the gestures used may be slightly off from what the platform is, like any sort of portability technique. But a hybrid mobile app takes basically a mobile web app and packages it for deployment directly to the device. And this is kind of the classic example. There's a couple of platforms that do this, but the one that I tend to think of is Apache Cordova, where we literally take our web application, drop it into a particular directory in the Cordova project called web, and run it through a processor, which is what Apache Cordova is, that generates the deployment binary for the device in question. And so I can take this web app and say I want to package this for an iPhone, or I want to package it for an iPad, or for an Android device, or for my playbook. And then I can install it directly on the device. And the advantage of that is, of course, is, you know, it's like an app, right? It's always there. I don't have any latency when it downloads. It also has slightly improved access to the device. There's like a native bridge functionality. And the native bridge functionality in Cordova, for instance, allows you to access system devices in JavaScript. So you have a set of APIs that are in JavaScript that let you access things like the camera, or the sound system, or the accelerometer. And so we get improved access to the device because fundamentally it's a native app. It's just that we're using a JavaScript interpreter to run it, and we're using HTML5 to sort of display things in the native app. And you know, that hybrid mobile app is quite commonly available in mobile platform app stores. So actually, if you use the app for Facebook or for Twitter, it's not actually written for you know, for iOS. It's actually a hybrid mobile app. Yep. The hybrid app tools and frameworks, Apache Cordova is the real common one, which is Adobe PhoneGap. Adobe donated it to the Apache Software Foundation, and it's actually done quite well. Ionic is another one. There's React Native, Sencha Touch 2. There's an Angular native. So hybrid apps are becoming quite popular. Now, the fact that the front end now is sort of having to communicate with the back end in terms of RESTful APIs, well, that does a couple things. It drives us to have to, you know, have no choice but to present functionality out on the open internet, which quite often means that we've got to get, you know, we've got to take into account our firewall and our network architecture. We also, you know, the fact that we start having RESTful APIs kind of drives us into a service-oriented scenario and drives us towards, in fact, microservices. So at a certain point, you want to think about partitioning your application server into separate services that we can factor out and run independently, because then, you know, the fact is that the phone just wants to say, okay, for this user, what resources do I have available? So that is the same across half a dozen applications that you may have. No point in having a separate, implementation of that inside every backend for front end. So it kind of drives us towards a service-based approach, and being RESTful and being relatively contained. That sort of says microservices all over it. So as an added value, microservices can help with things like resistancy to system failures and system scalability. And the one thing you have to deal with is the problem of the same origin policy constraint when we're connecting from the client portion of the RIA app. And there's a couple ways we can do that. We can use a reverse proxy setup to allow access to other APIs, or there's actually some headers, the same origin header that we can include in that API that says it's okay if the data that's downloaded is loaded by code that comes from here. So how can microservices help? Well, development of microservices can be done in smaller teams. Microservices are typically smaller pieces of software, each one of them. By definition, we need an interface for them. And if we're careful, we can do a well-defined interface. And if we have a well-defined interface, then that gives us loose coupling that allows us to deploy and maintain each microservice as an individual entity. So it becomes easier to view and treat applications as distinct products with encapsulated functionality. And it's been argued that having a product that a team is responsible for over time leads to sort of closer attachment with the product, or better ownership of the product, which then gives you better quality and other intangibles like unity of development vision. So you get better alignment between IT and business needs. And so product-oriented microservices are built around and aligned with business capabilities. So business capability is defined by the set of some product X and product Y, and et cetera, and so on. Now, microservices can be written in different languages, and so were macroservices when we did SOA, although it's kind of funny. With sort of big picture SOA, I always used to ask people, okay, so we got all this effort of defining things with XML and WSDL, and we do that so we can use different languages. And so I'd ask, okay, so what languages do you use? And 95% of the time people came back and said Java. Actually, but I think I worked out as like 80 to 90% was just Java. 10% was we used Java on the back end, but the front end people like VB.NET, so we used .NET. And then one or two cases in asking people this for 15 years, people actually said, yeah, we have a variety of languages implemented in our network. That has been changing with RESTful services or RESTful APIs, though, because the RESTful model sort of starts with a direct focus on the data that we're passing rather than the implementation. And so it's more common to see a mixture of services or a mixture of components that are implemented in different languages. So you may see a front end that is using Node.js as a switching system and Java storage or what have you. So we see a lot of different connectivities. RESTful APIs, we have other formats as well apart from RESTful APIs. The thing with RESTful APIs, they are based on a hypertext transfer protocol, which is a request response protocol. It's not designed for efficiency, really. It's designed for interoperability. If we have other problems or other concerns around interoperability, we may want a streaming protocol. Wire level protocols like AMQP for messaging have become quite popular. There's also data interchange formats like Apache Avro, Apache Thrift, Google's protocol buffers. JavaScript object notation is almost a de facto standard for RESTful APIs. Occasionally, we still see XML as well, but not as much as we used to. So microservices are very, very commonly the way to go these days, especially when we sort of combine that with a lot of organizations are finding a lot of value in moving towards flexible deployments in the cloud and having less and less sort of dedicated hardware. AWS Lambdas, or what we call serverless services, are becoming popular. The idea with an AWS Lambda is instead of creating an application, you actually just create what's basically a function call that will be executed when a request comes in, and then deploy that little piece of code into Amazon Web Services and let the web service infrastructure, the AWS infrastructure, invoke the code somehow when the request comes in. So that's something to have a look into. And there's been a lot of excitement around serverless implementations. I think serverless is kind of an interesting thing. We'll see it growing, but I think the applications are still going to be around for a while. So microservices architecture design principles are close to SOA. But the big difference in microservices is that we want to take into account operational aspects like deployment, upgrading, decommissioning of older versions, and scheduled maintenance. This is kind of one spot where sort of traditional SOA kind of fell down, which wasn't really resilient to changes in the deployments very much. So microservices are cohesive and loosely coupled. Microservices work toward a common goal. But one of the big things in microservices has been the idea of a flexible and dynamic architecture, so that we have load balancers that automatically discover services and load balance between them. We have service discovery protocols. We have network routing protocols and clustering protocols that allow us to have deploy more instances of the services as we need them, and then remove them when they're not being used. Decentralized processing, there's a single service or facade that's used by remote clients, and then that facade ends up breaking out into decentralized data. So microservices architecture patterns are about decentralized data management, where the functionality of the centralized service is broken into multiple services that actually carry out the required functions. And then microservices implement the functionality so that when we make a change to the functionality, we're only really talking about one application, we're not having to redeploy large swaths of application functionality. So decentralization may break data processing consistency and synchronization, however, and so commonly we have to have some kind of coordination, and we may need to deal with a single point of authority. That single coordination service then has to have high availability quality of service in place. The big thing to remember with microservices, here's this idea of boundaries again. Okay, crossing boundaries in a microservice is expensive. I'll just mention, there's always a couple of resources I like to point out to people. The one is the 8 fallacies of distributed computing. And this is the idea of, it's expressed by researcher at Sun named Peter Deutsch back in the 90s, and things haven't changed a whole lot. He said that when people start designing network systems or distributed systems, they tend to make a few mistakes. They tend to assume the network is reliable, that latency is 0, bandwidth is infinite, network is secure, the topology is always the same, and there's only one administrator, and it doesn't cost anything to move data. And he said, basically, all of these things turn out to be untrue, and fixing the resultant assumptions that are built into your systems can be expensive and difficult to do. So, there's lots of discussion of the 8 fallacies out there. The other resource I'd like to point out is something called A Note on Distributed Computing. Getting harder and harder to find, but here's someone stored a copy of it up on GitHub. And this was written by Jim Waldo, Jeff Wye, Dan Woolrath, and Sam Kendall. These are the people that wrote most of Java's remote methods invocation implementations, and they're also the people behind a networking infrastructure called Genie that Sun proposed starting around 2000. And that's actually where I came about it. Jim Waldo was the development manager on the Genie product, and also the chief architect, I think. So I had some interactions with Jim. I did some work on Genie-based applications back in the day. Actually, Jim Waldo, I asked him one time if you were trying to hire distributed systems engineers, what would you look for? And he came up with one of the greatest statements I've ever heard, which is that it's easy to train people who are smart, but very hard to smart people who are trained. And so there you go. Anyway, the point of this paper is to point out that we have to accept that because of network effects and limited failures and temporary failure, transient failures, we have to treat anything that crosses a process boundary, okay, anything that involves communications, is fundamentally different and a fundamentally different creature than internal method calls. And as a result, we see every now and then, and we still see every couple of years, programming frameworks which will try to use proxies or use interesting methods to hide the fact that we're making remote method calls or remote calls or network transactions, I guess, to be generic. And those systems are doomed to failure. So anyway, I strongly recommend, don't take my word for it, read it. It's about 10 pages. It's not overly academic, if you know what I mean. So really nice, nice reference, actually. What I will do, I will control copy that and drop it into the chat box, so that y'all can have a look at it. Similarly with the 8 fallacies. And yeah, I strongly recommend taking a look at that. So crossing boundaries or crossing the process boundary is expensive. When we're breaking down monolithic operations, you got to realize that anytime we do a network transaction, whether it's a RESTful API call or a message being sent over AMQP or a thrift transaction, an internal method call inside Java program is going to take somewhere on the order of hundreds of nanoseconds, whereas any network call is going to take tending towards milliseconds. I mean, a couple orders of magnitude difference in time. And as soon as we leave the process boundary or we cross the process boundary, we have the possibility of failures. And so we have to take that into account at the architectural level, not just at the code level. So crossing process boundaries is expensive. All right, managing microservices. You'll find that coordinating and managing the deployment may become an issue. You may be required to establish control over services lifecycle, centralized configuration management, logical to physical resource mapping, and so on. Service versioning. Generally, it's complex, multifaceted activity. There's a few possibilities out there. Some people use a centralized store of knowledge or distributed shared value store, like Apache Zookeeper is a popular one. Which offers services for highly reliable distributed coordination, centralized configuration management, distributed synchronization. The other sort of suite that is very popular is Netflix open source software. Netflix, of course, is the video streaming company. They have always been very open about their architecture, believe it or not, and they have published a lot of their sort of internal operating model as open source. And so the Netflix open source software suite includes things like the Eureka Service Discovery Platform, the Ribbon local load balancer, Hystrix to implement something called the circuit breaker pattern. And so there's a lot of good resources at Netflix. And there are a couple of, sort of platform as a service solutions like Cloud Foundry, even a lot of Amazon and Azure is moving towards platform as a service. So there's a lot of possibilities out there. Okay. So question. So the discussion about problems with calls over the network does not take away from the importance of microservices. Yeah, no, that's a good question. And the question, if I can kind of restate it, is Greg, you just told us that there's a problem with making calls over the network. So how does that sync with, the drive toward microservices? And the answer is yes. The important thing is that microservices offers us the possibility of having the representation of our system decomposition reflected in the runtime. Okay, which is a good thing, because that means that my components, my systems and subsystems, I can maintain them separately, I can deploy them separately. But the thing is, I have to take that the sort of constraints of the communications into account when I am designing the system. And that's not it's not a value judgment. It's not a good or bad thing. You got to know this thing. And so that means that when I'm, for instance, designing the data model for a microservice, I've got to be a little sensitive to what's the communication path. Am I communicating between two microservices that are in the same data center? In which case, I know that, yes, it's an order of magnitude slower than an internal method call, but it's going to be fairly reliable, and I don't have huge amounts of latency. On the other hand, is it going over a mobile network segment where I know that establishing the connection may take a long time, so I have an extremely high latency. If you're on a commuter train and you go to initiate an HTTP connection, you might have 10 seconds before you actually get the connection. And so that's, that defines a case where, number one, I have to do things that not do anything that someone else's timing is depending on. And number two, I got to realize that because of that sort of flaky environment, if I have, a 4 megabyte document that I'm sending, there's a pretty good chance it's going to get broken because I'm going to lose the network coverage in that 4 megabytes. So, it's just a question of you have to know what the environment is and design your interfaces to work around them. Okay, that doesn't reflect on the fact that microservices has a lot of advantages in terms of deployment and a lot of advantages in terms of management and really requiring the loose coupling that makes things maintainable. All right. Yeah, so here's an example here of typical kind of hardware architecture. Where we have a thin client that is talking to a web server, actually potentially several web servers, because it could have a load balancing kind of architecture. And then those web servers are communicating back to a monolithic stateful app. And it's sort of in a traditional web app environment. We have state contained in the application server. And that would be a large application that is deployed. We would have to have some way of managing for session affinity. In other words, if the client, the user is on a browser, and if the user is expecting to see stuff in their session, we have to make sure the next request goes to the same machine that has the session. And we may have to make sure that the session is replicated to other nodes in the cluster, so that if one node goes down, then we won't suffer failures. With microservices, Well, we might do things a little differently. Here's a rich client. In other words, an app on a device or a JavaScript app in a browser. And yeah, the JavaScript app in the browser has come from a web server, but it's, we've downloaded it once and we're not sort of going back and forth with code and content. Usually, we'll have a web server. The web server may have to maintain some state. Who knows? But then talks through reverse proxies to go talk to stateless microservices. Why is it the microservices can be stateless? Well, because the rich client now has enough intelligence in it and enough storage in it to hold on to the, the shopping cart that you're in the process of creating. And so we try to shift the state out of the back-end application into the front end, closer to the user where we really have state. You may even have a common state cache in the back-end application. There's a few ways about it, but we'd want most of our microservices to be stateless. Okay. Design for failure, distributed nature of microservices, we have to deal with design for failure because we have any sort of network activity has a chance of failure. And one of the sort of hallmarks of networks, and mobile networks in particular, are that networks have interesting and quite often transient failure modes. Let's see what time it is. I tell you what, I'm going to take 1 minute and tell you a short story, and then I'm going to wrap up. So we're not going to get to DevOps, but I want to leave a few minutes for questions. When we talk about interesting and possibly transient failure modes, I once worked in a company. I'll just get a little drawing tool here, and we were at this location, and we were building a new location down here, and eventually there's another location that was geographically going to be up here, and we were, over the course of about 2 years, interested in the DevOps. Yeah, unfortunately, we're kind of running out of time. So we'll sort of refer you to some other webinars that are on our website where we have recordings on the DevOps. Anyway, well, maybe I'll just skip over this and talk a bit more about DevOps. Anyway, suffice to say, we had this interesting thing where network connectivity between here and here, and we ended up implementing part of it with an RF link, and it was had this funny scenario where it would drop off the grid for about 5 seconds every now and then. We struggled with it for years, and then, well, 6 months anyway, and finally discovered that down at this corner was Pearson International Airport. And what was blowing away our network connectivity just for 5 seconds, about every 2 or 3 minutes, only on certain days, literally when the wind was out of the southeast or southwest, was that airplanes were stacked up, and if they happened to be using that runway, the ground proximity warning system would blow away our network link for about 5 seconds as the plane got overhead. So that's the kind of failures that you have to account for in a network scenario. So networks are prone to failure and possibly transient failure. All right. Yeah, so fault injection during system testing. Netflix talks about the chaos monkey. They actually go in and literally have a service that goes and blows away other services on a regular basis. Yeah, architecting in the cloud. Yeah, and I'll give you a quick overview of DevOps. The DevOps idea, short for development and operations, is an approach to delivering software solutions in a continuous manner. So we break down the barriers between development and operations, and manage complexities of enterprise apps by creating an environment and a pursuant architecture that supports really continuous deployment and continuous feedback on operations. And you can view DevOps as a culture across team software delivery discipline. typically, DevOps will cover development, testing, deployment, operations, and we use a whole bunch of tools to allow us to have continuous software delivery, highly optimized and as much as possible automated software delivery processes, and minimization of the number of software defects and unnecessary rework. How? By catching defects earlier on in the process and using as many automated tools as we can, and also what we call poka-yoke, which is a Japanese concept of mistake proofing, to prevent errors in deployments and production. Some of that is automation, some of that is building small checks and balances into the system. And all this leads us to software delivery cycle time reduction, work and process reduction, and risk reduction. So DevOps was originally referred to the practice adopted by operations to borrow process development or software development tools like putting admin scripts and version control. Now it really represents an approach to delivering systems, an approach to delivering software functionality, where DevOps is used in, the environment for delivering software. So development goals are aligned with those of operations, and not just about tools, but also people and processes. Infrastructure as code is a big part of it. I'm going to do a quick skim and try to point out anything that you should see. Collaborative development, continuous integration testing is critical. Continuous release and deployment is critical, and continuous application monitoring. This is the idea that it's hard to simulate applications in a complex deployment environment. So what we kind of have to do is monitor the applications and have sort of live monitoring of how the application's running in terms of response times and volumes through it, etc. Standing up DevOps. That you can probably look through. And containerization is kind of a technical discussion that I'm going to leave for now. There's kind of solution architecture in 2018. The essentials of solution architecture. We tried to talk about how SA fits into the enterprise architecture and technical architecture spectrum. And then we talked a little bit about techniques of solution architecture, primarily about decomposing systems and going through this analysis and synthesis loop of, decompose the system into components, analyze whether that proposed architecture is actually going to fit our functional and non-functional requirements, and possibly go through the loop again. And that decomposition is often sort of informed or guided by architectural styles and sort of architectural patterns. And then we talked a little bit about application architecture in modern times and the move towards microservices and RESTful APIs and sort of integrated front-end or rich interface applications. All right, well, that's great. Thank you very much for your time. I'll hang out here for a few questions if you want. Thank you. I know we were slated to go to 4:30, and people are probably playing around that, so I'm not going to continue on for too long. But thanks for coming, and remember, we WebAge do offer training and consulting and mentoring in many of these areas. So do please contact us and see if we can help out with your implementations. And I'll just answer this again. The webinar will be available offline, so that's good. And thank you for the kind words. And again, I think seems to me the slides were sent to you, and when the recording is ready, we'll let you know as well. Okay, there's a question on what are the other DevOps webinars that we have. And actually, if you just go to, I'll drop a link in here in a minute. I'm just going to find it. If you go to our website, there is down here in the corner a section here for webinars, and I've done a bunch of them, and actually all of our authors and instructors have done a bunch of them. There's a library of past webinars here. I strongly recommend two things. Well, I recommend you have a look at it on a regular basis, and I also recommend you have a look at the archived webinars. And the DevOps ones will typically be hiding. Well, there we go, DevOps. Okay, and you know, we have presentations on developing microservices, architecture, modern applications, DevOps for leaders, DevOps fundamentals, fault tolerance, test-driven infrastructure. Gee, it looks like I haven't done one for a while. Yeah, top trends in 2016 landscape. That was actually me. I remember doing that. And you know, agile and DevOps, and you know, there's a bunch of them on there. So yeah, well worth having a look at some of those, and you know, they're available. They're free. I think we want to get your name on a mailing list, so you have to register. But you know, we won't bother you too often. I promise you. As soon as we get you on there once, we won't send you multiple copies of things. Anyway, yeah, so have a look at past webinars and stay tuned for future webinars. We're doing a couple of these a month.